are supposed to find the moment of inertia of this right circular solid cone which has a radius r, height h from this axis perpendicular to its central axis about I, y dash we have to find out. So over here one thing to understand is that is, we say mass upon volume is density. It's a very elementary kind of thing which we all know. Density is denoted by rho. Total mass is suppose of this right circular solid cone is m. Volume is 1 by 3 pi r square h, though you can find it also through integration, basic integration also you can find this volume. If we take a small disk at a distance x of thickness dx, we have cut a section. Obviously its radius will not be equal to r. Let's say its radius is y and thickness is dx. So it is y is the radius, dx is the thickness. If we take these two triangles, one is this triangle, the other is this triangle. So y by x, that is tan theta. If we take it tan theta, so tan theta is same, perpendicular by base. So y by x is also equal to r by h. So y by x is equal to r by h. From here we say y in terms of r, h and x. So it is going to be r by h into x. So how we shall be proceeding is, our intention is to take a general disk of thickness dx at a distance x from here. We'll find the moment of inertia of this disk about this axis, that is ICM. And then what we shall be doing is, we shall be finding the moment of inertia of this generalized disk of thickness dx about this axis using parallax theorem, because this passing through the center of mass. We find the moment of inertia of this disk about this axis, and then we find the moment of inertia of this disk about this axis, and then we shall integrate. That is, moment of inertia of this disk about this axis plus this about this axis plus this about this axis and plus this about this axis. That is, x will go from 0 to h. Will integrate it. So that's why we may be having, when we find the moment of inertia of this disk about this axis, we may be having the terms like y also. So y can be replaced by x, and we can have just in one variable, and we can integrate x goes from limits 0 to h. That is how we are going to proceed. So number one, if we take this disk whose thickness is dx and radius is y, so obviously its volume is going to be small volume. Differential element of volume is area into height. We know that is volume of a cylinder is pi r square h, where r is the radius of the cylinder and h is the height. Similarly, the same pattern we are using over here, that is pi, instead of r we have y, pi r square. What is h? H is dx. So this is small volume of this. And mass over here, when mass upon volume is equal to density, so it means mass is equal to volume into density. So dm of this is going to be pi y square dx volume into density, where density is m upon pi r square h by 3. So we found that dm of this disk, we have found it. As we have earlier done, that moment of inertia of this disk about a diameter, we know that formula is mr square by 4, where m stands for the mass of the disk and r stands for the radius of the disk. Over here, the moment of inertia of this disk about this axis is, if we say ICM, is going to be m. M is what? That is dm. Pi y square dx into rho. This is m into r square by 4. Pattern will remain same. M r square by 4. What is r? R is y only. Its radius is y. So it is y square by 4. This is the moment of inertia. Or what? Of this about this axis. This is the moment of inertia. If you have found about I y dash, so it is going to be ICM, what we have found over here, plus, that is mass of this disk plus m into x square. That is what we do. And then we will integrate this whole thing from x is equal to 0 to x is equal to h, and we'll get the answer. So the moment of inertia of a right circular solid cone about an axis through this axis, it comes out to be 3 by 20 mr square plus 3 by 5 mh square. So this is the moment of inertia of a right circular solid cone.